طيب بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. Today inshallah in the lecture we'll be discussing impedance control. So we're still in the last topic of the course. We're talking about control of manipulators, of robotic manipulators. We'll be focusing mostly on fixed base manipulators, with the last lecture inshallah being dedicated to floating base ones, just to give you a flavor of how complicated these systems are. Now let's recap what we did last time, where we were looking at the N-link manipulator dynamical equations, and we have a control torque that we want to design such that we want the system to achieve stabilization. So we want to have like a desired angles for each joint that we want this robot to go to. We cast it into state space form, where the first state was the theta, all of the joint angles, and theta dot all of the joint angular velocities. The state space equation is given by this term, where we have the control torque being mapped to the system by this mapping g of x, and this is all the equations, the autonomous system, where everything relates the rate of change of x1 and x2 with the state x1 and x2. Okay, so if we don't have any control torques, the system is governed by this vector field on the state space. This is the summary of what we discussed last week, where we derived this control law based on a proportional term and a derivative term. The proportional term was given by the gradient of some potential function that we chose, psi of x1, and we have this derivative term just for injecting damping of the system, making sure we have asymptotic stability. The first term, the psi that we chose, had two terms, had like a quadratic term in the error between the actual angles and the desired angles that we have with some gain matrix Kp that we design. We also had the gravity compensation part that came naturally from this gradient of this psi function, because we actually chose the psi function, just I remind you here in the bottom, to be actually this quadratic term minus the potential function that we had in the original system. And this potential function, we didn't write it explicitly, but we said implicitly it's that whatever we differentiate, or whatever we calculate the gradient of, we get the gravity torque. Okay? Just like when you have the gravity torque on one pendulum, which is mg L sine theta, you can write it into some sort of potential function. In the end, this potential function is nothing else than mg multiplied by the height from some reference that you choose. So nothing fancy there. And the original original energy, total energy that we had in the system, was the kinetic energy and was the potential energy. So we just cancel out the potential energy, which leads us in the end naturally to have this gravity torque coming. Okay, and we have this proportional plus derivative plus gravity compensation controller. And in the end, we showed that this closed loop system, even though we had it there was a lot of nonlinearities in it, that we showed with this Lyapunov function, and again using Lassalle's invariance principle, that we have a asymptotically stable equilibrium point at the desired angles and at the zero angular velocities, so just stabilization problem. And we had global asymptotic stability because this is a quadratic function in the end. So you see, we have a quadratic function in x1, we have a quadratic function in x2. So everything is readily unbounded. And it was good so far. So I mentioned last time, just as an extra point. It's not important, but you will see it a lot. There is a very famous nonlinear control technique called feedback linearization. Okay, feedback linearization, the idea of it is very simple. Once you have a model, and it simply cancels out all nonlinear stuff. Okay, it uses the control torque that we have to kill all of the nonlinearities we have in the system, and by killing I mean it just compensates for it, just like when we compensated the gravity here. So gravity was one of the nonlinearities that we have in the system. If we go back here, so gravity is one of the nonlinearities, but we also have the friction, and we also have the Coriolis and centripetal torques. So if we can use the torque to cancel out all of these terms, we're going to be left out with some linearized system that we can design. And what is the best thing to do with a linear system? Design a linear PD controller, and it will make everything stable. So that's the whole idea of feedback linearization. And so if this is the state space model, so again, we have the torque here. I just put it all into one equation. So instead of having it plus g of x multiplied by tau, tau is simply how do you choose it with the feedback linearization mentality, is that cancel this, cancel this, cancel that. So you see, I have this term, and this term. And then in the end, I add the m inverse such that, okay, I have this extra term. I'm not canceling it. I'm just adding everything in this bracket to be multiplied by n inverse such that we have this closed loop system. And I think the closed loop system should have, we can either have here to be, yeah, I think we can have here just m. Okay, sorry, this is a typo. So we can have here the m, and in the end, we have something that looks like this. And this is a very simple linear system. It's easy to check whether it's stable or not based on the values of Kp and Kd. And this is a globally asymptotically also stable at the theta desired. So this is, you can always do that for any nonlinear system. What do you think the problem is of this? And just another point is that this is usually in the robotics community. This is known as the computed torque method. Okay, it's computed torque method, and in other literature it's just called the inverse dynamics control. And you see why? Because we're inverting the whole dynamics. I have the dynamics of the system. I know it through modeling, and I'm just killing all of it. I'm just inverting all of the dynamics. Whatever was plus is minus. Whatever is multiplied, I just multiply by its inverse and so on. So I'm just inverting all of the dynamics that I have in the system. What do you think the problem of this controller is compared to the other one that we had?
Depends on the model of the system.
But the other one also depends on the model. Which one depends more on the model? This one, because in the original one, so in the PD plus gravity compensation, the only nonlinearities we needed to know was the gravity term. But now I need to know also C of x and B of x. I need to know them very well. I need to know also the mass matrix. And you see, these are not just some trigonometric functions. They also include the parameters of the system. They include the mass of the links. They include the inertias. They include the joint friction. They include the length and so on. For some complicated robot, this might be not that easy task to get all of these parameters, and I might be having all of these uncertainties. Even if I have a model of the system, these parameters, we identify them through experiments, and we have a lot of uncertainties in trying to find these parameters. So just as a comparison, when you look at the computed torque method, you're going to find that, or the feedback linearization, what it does is that it does full dynamic compensation. It kills all of the nonlinearities. But when we use the Lyapunov analysis with this idea of having this proportional derivative control and it only cancels out whatever we need so that the system is asymptotically stable. So, and this is the best thing about Lyapunov stability. It identifies you through this Lyapunov analysis. It tells you what are the good nonlinearities between codes and the bad nonlinearities. The bad nonlinearities, like the gravity, we have to cancel out because we cannot live with them. But the Coriolis term and the friction term, there was nothing wrong with them. So when we did the Lyapunov analysis, if you remember from last time, the friction term wasn't any problem because it's actually damping the system. So it's naturally making the system asymptotically stable. So there's nothing wrong. If it's nonlinear, there's nothing wrong with it. What about the Coriolis term? Does anyone remember what happened to it when we were doing the Lyapunov analysis last time? Exactly. By looking at the relation between C and M dot, so remember M dot minus 2C was actually a skew-symmetric matrix. This was exactly the same for the same deep geometric reasons I never discussed. That you remember when we looked at the rigid body rotation, remember the gyroscopic term that had the skew-symmetric form of the momentum? It also just disappeared from the equation, even though it was nonlinear, but it also disappeared. So all of these skew-symmetric, whenever you see something that's skew-symmetric, always know there's some deep geometry behind it, okay, just as a side note. So this skew-symmetric term, okay, again, so it's part of a skew-symmetric term, so C is part of the M dot minus 2C. You see it also, it's a good nonlinearity. So skew-symmetric terms in the Lyapunov analysis means that there is no energy, neither created nor destroyed. It's just some routing of the energy going back and forth. That's why it just disappears from the energy balance when we calculate it. So the computed torque method or the feedback linearization kills everything. The PD with gravity compensation kills only or compensates only what we need. In terms of performance, the computed torque can definitely get very good performance, can get very fast, accurate trajectory tracking if you want, if you really know the model, and this is the if. If you know the model, you can get good performance. If not, you're actually injecting error in the problem, okay? Because you're compensating something. So let's assume that I think that the length is 1 meter, but the length is actually 0.91 meters. Okay, so I'm actually adding error through the torque. I'm not canceling it. And these partial, like these uncertainties can make the system unstable if they are really that large. While the performance of the PD with gravity compensation is not that good when you look at very dynamic cases, but for slow or moderate speeds, for stabilization, actually it outperforms the computed torque method. And the major issue, and this is the issue of the model dependence with the computed torque or the feedback linearization, we are depending a lot on the model, so we need to know everything in it. But here we're less sensitive to all of these modeling uncertainties. So this is just a side note. Whenever you see something that I have nonlinearities, let's scale it out with the controller. You're going to always have the same problem. And this is the main idea of feedback linearization. While when we're doing the Lyapunov analysis, or we're using this energy of the system to guide us during the Lyapunov analysis, we canceled out the minimum necessary stuff. So this was just a side comment or an extra part on what we discussed last time. Now let's move from the motion control mindset to the impedance control. This is something I'm pretty sure is new for all of you. Who here heard of interaction control, impedance control before? Okay. Only one, two, okay. So it's very new, and it's particularly only for robotic systems. So we're not dealing about, so we don't do impedance control for non-robotic systems for the reason I'm going to discuss now. So now let's start with this idea of comparison. Let's compare trying to justify why do we need this paradigm shift. You all know what paradigm shift means? What is a paradigm shift? No, right? Fancy word, okay. It's just a fancy word for saying you need a change of mind. You need a different way of thinking of the same problem, okay? So whenever you have a robotic system, the first thing that comes into your mind is what? Let's do control, right? So let's do, I don't know, state space modeling. Let's do transfer functions. Let's do single input, single output stuff, fold placement. And you say it all doesn't work, right? So you cannot think in terms this way, right? Let's think of, what about disturbances? Let's reject them. Okay, let's kill them, let's reject them. It doesn't work. For robotic systems, you cannot go to the robotic control problem with this mindset. You need to think of it differently. And this is the reason. When we have a motion control problem, like for example, a satellite radar or tracking, I don't know, system, the main objective when designing the motion controller is that we want to achieve stability and we want to reject the disturbance. And we want to maximize performance. So we want to have, I don't know, like fastest rise time, fastest settling time, no overshoot, all of these stuff. But when we're doing with interaction of robotic systems, what we want to have is that we want the robot to be able to interact with an unknown environment. This is very important. The environment we're acting with is unknown. And by unknown doesn't mean that the robot doesn't know what it's dealing with. That usually happens, okay? You can do stuff while your eyes closed. So we can have this, like, we can deal with stuff while we can interact with stuff without having even sensory information. We can do that. But what's most important when we're dealing with robotic systems is that we need to have stability. And there's something even more than stability, and it's even more important in practical stuff, which is safety. And safety is not the same as stability, okay? So that's one point. The other point is that when we talk about motion control, when we want to design motion controllers, we're actually thinking of closed dynamical systems. Any disturbance is something that's external, coming from the outside world, and we just need to kill it. We need to reject it. And when we're doing stability analysis, we assume that there is no external inputs coming to the system. Otherwise, because we're using the closed loop model, and the closed loop model is the controller and also the system that we're dealing with. When we're dealing with the interaction control, we want to have a design of a controller for an open dynamical system. And by open here, we have external forces, we have external torques, we have external wrenches acting on the system. And they're coming from an unknown source. We don't know what the environment looks like. So if you want to do any stability analysis with the closed loop, which is the controller and the system, we need to make some remarks on what happens to this unknown environment. And because it's unknown, we cannot model it. And this is a big problem that a lot of people fall in this problem or in this pitfall, is that they try to model the environment. Say, let's assume the model is a spring and a damper, and let's live with that. And you cannot do that in practice. It's a very simplified view of the world. When we're dealing with motion control, we say, okay, you draw a block diagram and you say, I have as an input to the system, to the robot, a torque, and the output angles, right? Or angular velocities. You think of it this way. When we deal with interaction control, the same also for a drone. When you say I have a drone, I say I apply the thrusts from the propellers as an input, and I have the motion of the drone as an output, right? So the whole twist of the drone and the pose. When we're dealing with interaction control, it's not enough to think about of these unilateral signals. You also need to think about bilateral signals. This was something we always emphasized throughout the course about the duality. Remember duality between forces and torques, between forces and velocities, between torques and angular velocity, between wrenches and twists. It will be very clear in this part when we talk about interaction control. We don't need to control either velocity or force. What we're actually going to be controlling is the relation between both, the behavior of the system with these two parameters. So we're always going to be thinking in terms of duality, in terms of these two control signals. So with interaction control, so this is the typical example when you have, or typical task that you would have when you're doing interaction. The first one is it's called a peg in a hole. You're trying to insert something like a key, for example. When you try to insert a key, this is a very hard problem. You don't appreciate how hard it is because you do it very naturally. Try to ask a 3-year-old to do it, and you're going to see how hard it is. Okay, takes years to learn this simple task. Turning a crank is also very hard. Okay, because if you have friction, if you have column friction, if you have static friction, it becomes very difficult, right? You do it naturally. So if you have something that's stuck, you apply a lot of force, and then you lose it, and then you start moving very naturally. You do it without thinking. Trying to program a robot to do this is very difficult. That's if the robot was only on a fixed base. Now imagine if the robot was on a floating base. Imagine if the robot was underwater or in the air, things become more complicated. So if we try to use the motion control mindset to do interaction control, which is controlling either the pose, the position and the orientation, or the wrench, the force and the torque, requires perfect knowledge of the task. I need to know precisely how the task looks like. Okay, so what is the dimensions of this peg? What is the dimensions of the hole? How much clearance is there in between them? But not only the geometric dimension, I also need to know mechanical properties. So these are two mechanical systems. So there is friction. Whenever I slide one into the other, there will be friction between both. Okay. If there is a little bit of misalignment, if I have 1 degree of angle, okay, it will not enter. So you see, it's very, okay, I need to know precisely how the task looks like in terms of geometrical and mechanical properties, and that's not possible in practice. So going with a motion control mindset, means you need to have a perfect model of the environment, and this is not practical. What we do in interaction control, okay, or in impedance control, as we're going to be discussing, is that we control the behavior, which is between the wrench and the pose. So we don't control either the pose nor the wrench together or separately. We control the behavior between them. We're thinking in terms of what is the map or what is the behavior that relates the wrench and the pose together, and we try to control this behavior. And this led to, okay, this idea, okay, was what was discovered by, not discovered by, he's the first one to actually bring this into the field of robotics, was Neville Hogan. So Neville Hogan is a very well-known scientist in robotics. He had this triple part paper. Okay, it's called Impedance Control and Approach to Manipulation. It has part 1 on the theory, part 2 on the implementation, part 3 on the applications. The second one is only cited 7,000 times, so it's not that much. Okay, he's a professor at MIT. Okay, H index of 100, so not that fancy. So this idea of impedance control. So where did he get this idea? So who here heard about electrical impedance before? So this term should ring a bell if you had any electrical engineering background. So this should ring a bell, right? Impedance. The opposite of impedance, you also might remember, it's called admittance. Okay. In the electrical engineering setting, so impedance, just as a reminder, is the ratio between voltage and current. As simple as this. But it depends on what is the input and what is the output. Usually this is how we define admittance and impedance. So impedance is the ratio between voltage divided by current. So it is whatever current is multiplied by such that we get voltage. And admittance is whatever voltage is multiplied by to get the current. Okay, so we have they're just one over the other. They're reciprocal of one another. Impedance is you can always think of it this way. So impedance is actually a total opposition that a circuit, okay, which can have resistance, can have inductance, can have capacitance, more complicated stuff. But is the impedance that the impedance is the total opposition that a circuit offers to the flow of some alternating current. Usually we talk about the impedance when we have an AC current, when we have an AC circuit. And this is, I remind you, when we were discussing phasors. Okay, if you took an electrical engineering course, this makes sense. If not, this is just a side remark. So phasors were exactly the same as polar coordinates. We have a magnitude and a direction. So the magnitude is given by the norm of this variable, the voltage and the current. And whenever you have an alternating current, then we have this direction that's changing all over the place, and we have this phase shift phi I and phi V for the voltage and the current. This is with Euler's equation, you can write it as the cosine plus the J sine. Okay, these are just some stuff you should know from if you had any electrical engineering course. And if we don't have any alternating current, we're just looking at DC, then the impedance is nothing else than the resistance, right? So voltage is equal to V is equal to I multiplied by R. If you don't have any alternating current, if you have capacitance and inductance, then depending on the frequency, they change the value. So this is J multiplied by the value of the reactance. So all of this is what electrical impedance and electrical admittance is, just from electrical engineering. There is something by analogy, the same for mechanical systems, and which is the mass spring damper. Think of it this way. So mechanical impedance is also the ratio between force and velocity. Just like the electrical impedance is the ratio between the velocity, the voltage and the current. So voltage is some sort of like potential, okay? And the current is the flow of all of the electrons inside of the wire. So also here we have some sort of flow, some sort of velocity variable, and we have some potential like function, some force that's acting on the system. So the ratio between the force and the velocity, we call it mechanical impedance, and the opposite, we call it also mechanical admittance. And you can also imagine it will depend on the value of the mass, the value of the stiffness, and the value of the damping. And everything here works in 1D. So this is a 1D case, extends trivially to 3D. It also extends to 6D, but when we're talking about 6D, we're going to have a 6D spring, a 6D damper, and a 6D inertia. We know what the 6D inertia is. It's the generalized inertia tensor. But what is the 6D spring and what's the 6D damper for next time, inshallah? So this is also something you might have done before, okay, which is it's clear what the impedance is, because here we depend on the time, or we depend on the frequencies. If we look at the Laplace, okay, domain, then we can rewrite the position of this mass multiplied by the mechanical impedance will give us the force. And this is nothing else than, okay, just the Laplace transform of this equation. So the dots are represented by S. So here are two dots, S squared. One dot is the S. No dots, then we just get the variable X of S. Okay, so this is just a reminder of what you know. If you know it, that's okay. If not, this is all just motivation of where we're going. What you need to look at here is that what's the difference between when we say admittance and impedance is that when we have impedance, we have the motion is an input, and motion here is either the position or the velocity. They're just the time derivative or the time integration of one another. And we have the force as an output. Okay? So you see the relation between position and forces, or sorry, forces and position, or pose and wrench, or torques and angular velocities. You always have that. And if you have the pose or the position is an input, you have that the force is an output, then the mapping is called the impedance, and the inverse is called the admittance. When you have that the force is the input and the motion is the output. So far, so good? Okay. Now let's look at what the idea of impedance control for robotics, what it is. So Neville Hogan's idea of impedance control is that we are not going to command the exact position or forces that the robot should have. What we're going to be doing is that we're going to be controlling the robot to behave, and this is the code, between quotes, we're going to wanting it to behave as like a mechanical impedance. So how does it behave? how can we say that the robot behaves like a mechanical impedance? If it responds to external forces with a desired relationship between the force, the position, and the velocity, just like a spring and mass and damper system would behave. This was the idea. And the key idea that we do when we're doing impedance control is that we're shaping the robot's dynamic behavior. So you see, we're not controlling the position, we're not controlling the force, we're shaping how the dynamics of the robot should look like when interacting with the environment. And by doing that, we don't care about what the environment is. We're just focusing about the behavior of the robot. And then we choose these parameters, the spring and the damper. And here, the spring and the damper will actually be controlled. So there will be a virtual spring and a virtual damper inside of the controller itself. It will behave as if it's a spring and a damper. So the controller will behave as if it's simulating a spring and a damper in the real system. And the overall closed loop system, which is the robot plus the controller, will behave as a mass spring damper system. Again, just the usual drill. Let's look at how it looks for the point mass, and then let's extend it to a two-link manipulator. And next time, inshallah, we're going to go more complicated. So this is just the intuition of what the impedance control. And at the same time, so this is the intuition, but just as a remark, there's a very big chance this also might confuse you, okay? Because it's too simple that it will confuse you with something else that we did. So keep that in mind. So this is what impedance control is. This is just the mentality. So we have our system that we're interested in is just a point mass. So this is our system. This system, we can control it by some control force, and it's interacting with the environment. So there is some sort of force that comes from the environment acting on it. So there are forces applied to the point mass from the environment, and there are forces applied to the point mass from the control. In both cases, we need to identify this idea of duality. We need to look at what is the dual variable of the control force is the velocity of the point mass. What about the dual variable to the interaction forces is also the velocity of the point mass. This is the duality between forces and velocities. The equations of motion of a point mass with no gravity are as simple as psi dot is equal to V, and mv dot is equal to the force from the controller and the force from the interaction from the environment.
When we say duality, we just mean on dual what's it called, species. That's all.
This is one point of duality, the geometric duality. There is also the power conjugancy, in the sense that when you pair these two, they are both live in dual spaces, right? So one is a covector, one is a vector. So I can always take the pairing between them. What do I get? I get a scalar number. Whenever you take the scalar number, this pairing between the force and the velocity, what is the units that you get? Power. You get mechanical power. So this is the duality that we're looking for. Okay. This is also the same duality that we have between the voltage and the current in the electrical sense. Duality between voltage and current. What does it give you? Electrical power also. Yes.
The velocity in this case scenario, is it both velocities, are they different?
No, the same velocity. The velocity of the body. So you see here, this is so both of them affect the velocity of the body. That's it.
But then both of them leave, they are both vectors, but they live in their own spaces.
Yep.
But then we have a single vector that lives in a dual space to each of them.
Yes. So what is the rate of, so if I multiply this by V transpose, what do you get here? So if I multiply this by V transpose, what do I get on this side? The rate of change of kinetic energy. Kinetic energy is half m V transpose V. So when I differentiate that, I get m V transpose V dot, which is this term. So if I multiply here by V transpose, I get here the rate of change of kinetic energy. If I multiply here by V transpose, I get the power that comes from the controller, and here by V transpose, I get the power that comes from the environment. So you see? So the V transpose multiplied by this guy is the power, V transpose multiplied by that guy is power, V transpose multiplied by this guy is the rate of change of kinetic energy. Okay? So the goal of the impedance control is the following. We want that in the task space, so the task space behavior, in other words, how the interaction, okay, how the interaction force or interaction force and velocity, both of them together, okay, we usually give them a name of a port. So both of these together, we give them the name of a port because they are dual variables, okay? And I take the pairing between them, I always get power. So this is what's known in the port Hamiltonian literature as a port as a port that you connect to the system. You see, the port now is not one signal going aside. We're always thinking about this bidirectionality of two signals. So the mass, the point mass, which is our system, is connected by this port to the environment and by this port to the controller. The controller, we want it to be as if it's a spring and a mass. And we want that the closed loop system, which is all of this together, to behave like this. We want to have mq double dot plus bq dot plus kq is equal to the interaction force. What does this remind you of? A mass and spring damper equation. What is the q here? The q is just the two ends of the spring. On one side, we have the position of the mass, and on the other side, we have the end point of the spring. You always remember that the force applied on a spring is minus k delta x. You always have delta x there. Okay? They are the same whenever one of them is whenever you have one of the ends is fixed, okay, to the origin, then you have that's minus kx. But whenever you have both of the sides of the spring are moving, let's say, for example, that the spring both are moving with the same velocity, so they always maintain the same position. So what is the force applied on this by the spring? 0, because delta x is 0, it's not moving. And then if the spring starts to move, you start to get this force due to the spring. So q here is the elongation of the spring, and taking the time derivative of it is psi dot minus psi desired dot. So psi dot is the velocity, and the second derivative of it is the psi double dot, which is the v dot, and psi desired dot double dot. So this is how we want the system to behave. You see where we're starting with the impedance control. We start, how do we want the system to behave? We want it to be, and by system I'm talking about the closed loop system, right? So the whole behavior of the closed loop system, the controller plus the original system. We want it to behave like a mass spring damper system with respect to this power port, the external one. Compare both. If we want that the closed loop system should look like that, and this is our original system with the controller, how should we choose the control equation, the control law? We choose it like this. Okay? It's very easy. It might look very complicated now, but if you go back, it's 2 lines that you can prove it for yourself. Okay, take this expression. So this is psi desired double dot, okay, which is, and this is m psi double dot. Okay, so m psi double dot, and I have here m psi desired double dot. So m psi desired double dot minus, if I bring this to the other side, minus m psi desired double dot, I get mq double dot. So that's the first thing. When I have here minus b v minus psi desired dot, I put it to the other side, it becomes bq dot. When I choose here this to be minus k psi minus psi desired, and I put it on the other side, it becomes k psi minus psi desired, which is the q. Okay. So in the end, just plugging this controller in this equation will lead this closed loop system behavior, this impedance controller. You want to work it out? Yes. Okay. Let's do it. Let's see. So the original system, so it had mv dot is equal to f control plus f interaction. The mv dot is the same as m psi double dot equal to this term. We said that we want the f controller. We chose it to be psi desired double dot. We had then minus b psi dot minus the psi dot or the v, this or the v, they are both the same, minus the psi desired dot minus k psi minus psi desired. I can rewrite this equation as this term minus b q dot minus k q. You agree?
Where with the if control? Like this
If we choose it like this and plug it in there, see what do we get?
if we choose like choice, or
Yeah.
we or based on the system.
No, it's a choice, and there's also a mass here. Yeah, it's we chose it based on the model that we have, so we just calculated it from it.
So our choice comes from how we want the system to behave in
Yeah.
each our cases, the spring mass spring down.
Our system, you mean the closed loop one or the original one? The closed loop is we want it to behave as a mass spring damper. This equation will make it behave as a mass spring damper, as you're going to see now. So when I plug in this part, I get m psi double dot minus b q dot minus k q plus the f interaction. So just put all of these terms on the other side. And remember that the q was actually defined as psi minus psi desired. The q dot is the psi dot or the v minus psi desired dot. And the q double dot is the psi double dot minus, or the v dot minus psi desired double dot. So in the end, you see we're going to have mq double dot plus bq dot plus kq is equal to f interaction. So you see, this is the control law. And when I plug it in with the system, so when I look at the closed loop system, this is the closed loop system. You see the difference with what we did earlier? The closed loop system has what? Has the F interaction. We're not thinking as F interaction is something that's not existing, that we assume it's zero, and then we do Lyapunov analysis and so on and move on. No, it exists. And this is why we want to shape the behavior of the system. We're always thinking about this guy. We're always thinking about the interaction. How would it feel the system or the closed loop system? And we're always thinking and doing analysis with respect to this interaction port. This is the mindset between the interaction control and the motion control. Okay? And it's only a mindset, and I'm going to show you now why. Okay. So when we have this controller, and now let's look at, okay. When we look at, sorry. No. Yeah. So now let's look at how do we do the interaction. So far in this cartoon figure, we have that this is the system. This is our point mass. Forget about this, because the spring and the damper, do they exist in real life? They are virtual. They are virtual physics that we're using the controller to simulate. What we only have here is a force applied by the controller. In other words, we have something that can move the mass around. I can move the mass around. I can make it move, okay, with some control force. And this is only how we simulate it. The psi desired is, you can think of it as the set point that we want this robot to follow. It's not a physical set point. It's not an actual set point. It's a virtual set point. You're going to see now why. So if you move the psi desired in this way, what will the point mass do? It will follow you. Okay, so if I go to this point, whatever the spring, you remember what the spring will do? It will always try to make sure that psi and psi desired are the same point, right? So that they converge to each other. So if I move the psi desired like this, and I start the simulation, or I start looking at time as progress, the mass will follow the psi desired. And of course, it will start to oscillate depending on the value of k and b. So you can imagine that this is what will happen. So this is the psi desired, this is the point mass, and then it starts to do something like this. But then if I take the psi desired, it's my set point. I can move it around as the operator of the robot. I can move it around to inside of the wall. So this is my psi desired now. What will the mass try to do? It will try to do what? Penetrate the wall. Will it do that? No. So what is happening there? Will it reach the psi desired? No. But what is it trying to do now? To push more force, exactly. It's trying to push more on the wall. If I go back with psi desired more, it's going to try to push more. If the gain of the stiffness that I have inside of the controller, remember, this is a controller, okay? That it's simulating a controller, this K. If I make it higher, what is happening to the force applied to the interaction? It's getting also higher. So you see, in the end, when we're looking at the static interaction case, which is, so we're now at a contact phase and we're not moving a lot. So Q and Q dot and Q double dot are zero. So we're not moving at all, no acceleration and no velocity between the psi desired and the actual mass. But there is just a difference, an elongation of the spring, of the virtual spring, which is the distance between psi desired and psi, the relative distance between them, and multiplied by the gain that I have in the controller will give us the interaction force. So if I want to have an interaction force, I would just either move psi and psi desired or make the gain higher. What is the minimum psi minus psi desired they require? What's the minimum number that you require? Has to be bigger than 0, right? Has to be bigger than 0, because if I bring it on the other side, if I just bring it before the interaction point, just before it, okay, infinitesimally, will there be any interaction force? No. If I bring it to this side, will there be any interaction force? No. So I have to be on the other side. So psi minus psi desired, they have to be, okay? So again, depending on the sign, okay, how you define. But the psi desired needs to be inside of the wall, and now you're going to be pushing on the wall. So the scenario that how we do impedance control is that if this is the end effector, in this case, just the point mass, and I have this is the desired frame that I wanted to go to, I'm going to choose the desired frame to be inside of the wall, and now it will start to interact. And you see now, if I have moved this, my desired set point, my virtual desired set point, I move it in this way, I'm going to move this way, you see? And now I'm following it, but not only following it, I'm also interacting, I'm pushing on the wall. So this is what impedance control is.
If we want to increase the force, like make the point fairer, or
Yes. Or make the gain higher.
The gain of the K.
Of the controller.
Why, if we make it further, why the force will increase? Of the equation. I'm trying to imagine a force into air. Like,
so again, that's the problem. You're imagining something with no interaction. You're imagining a force while actually there's no interaction. So you're thinking in terms of velocity, something that can move. And because of this duality is very important. If you have something that's moving, there are no forces. If you have something that's not moving, then there are forces. Okay. So if I'm moving like this, what are the forces applied to me? Nothing. If I take the pen and put it there, what is the force applied on the pen? It's mg, exactly. The force applied on it is mg. Okay, that's what. But there are two mg's actually. One is down and one is up. That's why it's not moved. Okay, but the force applied on it, okay, in this scenario was mg. Okay, because it's the interaction force. So if you look only at the interaction force, now it's mg, and now it's 0, because now I can move it. So you see, there is always this duality. Whenever there's a force, there is. Okay, whenever there is no force, there will be a velocity. Whenever there is a force, okay, the other way around. Okay, just yeah.
static interaction. What is dynamic interaction?
Dynamic interaction is that you have to go back to this whole equation. So this is what will be governed by the dynamic interaction. This equation. So when psi and psi dot are moving at the same time, okay, so they are both moving, okay, and so let's say for example you have something that looks like this. So this is dynamic interaction. Okay, the forces applied will not only depend on the spring and the damper, they also depend on the interaction forces. And the interaction forces are very complicated. Okay, when you look at if you want to model the interaction forces, you get into very weird stuff. By the way, Newton's law don't even follow these interactions, because whenever you have discontinuities, Newton's law fails. Okay, whenever we have column friction and static friction and all of these weird stuff, we have a continuity problem. We don't have smooth equations, so we cannot talk about first differentiation and second differentiation in time because of this discontinuity. So things break there.
What about the force interaction? It changes. It is not a specific value.
It's not a specific value.
But then it's,
This one.
we said earlier for the zeta d. According to the interaction, we can put it away for if I need more force.
Yes.
Or changing the k value of this parameter. So it changing according to what if I'm not measuring the interaction force. Or, actually, I'm measuring the interaction force or not.
There is no measurement here. I'm saying this is the actual whatever interaction force that you have, okay, in the system is given by this value, provided, and there's an if here, that you're not actually moving. What if this is not a rigid wall? What if this is a soft wall? Then if there's a soft wall and even I'm interacting, I'm gonna start pushing on it and I'm gonna start to move. Okay? And things will change there. This is also another example of dynamic interaction.
find the value of the K or the value of the desired configuration for getting this interaction force according to it?
Very good question. So the question is, how do I choose? If I want, so I think you're asking the other question. If I want a particular force, so if I want to push on the wall with 2 newtons, how do I make sure that the stiffness, okay, that I chose, or the side desired that I put inside of the wall will give me that interaction force? Exactly. That's a very good question. Next time, inshallah. Okay. But this only looking at here, we can affect the force that's applying to the environment just by playing around with the stiffness or playing around with this desired set point. This is the result of this. Clear? Maybe there was some question.
How we are doing the impedance control, we want to reduce and avoid the impact of the force.
Impact. So you're saying that if you're saying that we're moving very fast and then there's an impact, forget about impact. So let's say that we approach the wall very slowly. So we approach it very slowly until we reach that point, and then I started to move this also very slowly. You see, I'm gonna be applying more force to the environment. So even if there are no impacts in terms of a large momentum exchange, then we still have also this interaction force. Very good question. Okay, what happens now about the uncertainty of the environment itself? This is just the controller. How can we show that we actually are stable? So this is another point. So we're interacting now with the environment. This is our controller. So if we go back, so this is the behavior of the interaction, and this is how the controller looks like. But this is how the controller looks like. But who said we're stable? What about stability while interacting? And we're going to be interacting with an environment we don't know what it is. So how can we show that we're stable while we don't have a model of the environment? Also next time, inshallah. Okay. A lot of open questions. Okay.
Of course.
Yes. Okay.
Environment specific.
The controller doesn't care about the environment, and that's the problem. Some problem in it, because this is only how the interaction force applies. But what if the interaction force of the environment itself has some dynamics of its own? Imagine that a spring. Imagine that the environment itself has some stiffness. Okay, it's a soft material that when you're pushing on it, it has some frequency. Okay, it has some stiffness inside of it. And I'm also pushing with some stiffness. Okay, so I have stiffness of the controller, and there's the physical stiffness of the environment. Both of them coupled together, they might make the system unstable. Okay, so I need to, when I'm choosing this, if I don't know anything about the environment, how can I control it? So I must know something about the environment, and this is what we're going to be seeing. Okay, this something is called passivity. This will be topic of next time, inshallah. So this is just a summary, but now to confuse you even more, what does this remind you of? A PD controller. If we remove the side D double dot, and we remove the side D dot, what in the end, what do we get? Same PD controller. So are we doing PD control in the end? No. The starting point is completely different. Okay, and the goal is completely different. When we're designing PD controller, we thought about the error, we multiply by some gain, we took the error dot, and we got the controller. This was the same controller that we got when we thought about a potential function. We took the gradient of it, okay, and we took the damping injection. It was the same controller, but we got it from a different way of thinking, looking at this shaping of the energy, balancing of the energy. When we thought about the PD control, we were not able to extend it. We were not able to extend it to the geometric setting on SO3 and SE3. But when we looked at it from a potential point of view, okay, we managed to extend it and things worked on SO3. The same also here. When you think of the controller, the impedance controller in this way, from this perspective, and then you think about the complicated case layer, which is 6-dimensional springs and 6-dimensional inertia, this will work, but think of it this way will not work. Okay, so again, don't be deceived by the fact that the controllers look exactly the same or very similar. Actually, they are the same. We can actually have the same controller if we have a PD controller with trajectory tracking, because this will be just a feed forward term that we add. And if we add here just feed forward term to the PD controller, we get in the end the same controller. This is actually a nice story. So when Neville Hogan posted this work, published it. There were no posts that time. Okay, so it only published. Okay. So when he published it, actually some people came up with some reply article and saying, okay, impedance control is nothing else than PD control. And he replied back. Okay. And time showed that actually they are completely different. Because when we extend this to more complicated scenarios, when we look at more complicated environment, when we look at rotation and translation at the same time, this is what works out. Okay. When we look at, so we can go even much further than just impedance control. You're going to find a lot of extensions to it, and it's an active area of research. So that's it for impedance control of the point mass. Now let's look at how can we do the impedance control of the two-link manipulator.
I have one question. With regards to the interaction, for example, if we have a robot not touching the wall, for example, not directly interacting with it, we still have the effect of gravity. Is it not considered as well as force from the environment?
That is true, yeah. And that's why we need to compensate for it.
That means that we can actually do impedance control without having to have interactions.
This is already for the interaction, but what the interaction sense that we're thinking about here is that the interaction with an environment that you want to affect. Gravity, we always want to cancel it because we don't want the robot to just fall down. We want to compensate for gravity, and then we're going to have a gravity-free robot. Then we start thinking of the control. Last time, thinking about the control was just the proportional term and the derivative term. And the gravity compensation was, even in the feedback linearization, was also there. So also we canceled out the gravity. We're going to be doing the same here. When we look at the N-link manipulator or the two-link manipulator, we're going to be also canceling out gravity, and then start thinking about whatever extra controller you want to do with. So this is now the equation that we have, a slightly different. Yes. No. There's no tracking at all. Tracking is the same mindset as the stabilization, but with a time varying reference position. So you have the feed forward term, and you also want to reject disturbances. So if you want to do tracking, any disturbances are rejected. Okay. And this is why the next extension, let me go back. So the extension of the PD control is what? Whenever we have disturbances. PID. Exactly. But when we're talking about impedance control, the extension of it is not impedance control with an integrator. It's not how it works. You see, this is the paradigm shift.
I will start with PD control. Can I go for
impedance control? This is the impedance control. The PD controller is the same as the impedance controller without the feed forward. Okay. It depends on what you want to do with it. Okay. Try it in the simulation and let us know. Everyone will see option. Okay. So this is the two-link manipulator. So these are the equations of the two-link manipulator, should be familiar to you by now. We have only one extra term, which is interaction torques. We're not thinking about a robot that's in nowhere. Just we want to do shapes, to move from one point to the other. It's just motion control of robots. Robots, by definition, were made to interact with the environment. The word robot, all know, it comes from the word slave. So slaves are working by their hands. So the robot should work and interact with the environment physically, by definition. We don't want to have a robot just moving around and doing nothing. So we're going to be interested in how the end effector interacts with the environment. So we added a new frame. This frame is a body fixed frame to the last link of the robot. So we had here two links. So we had frame 1 at the center of mass, frame 2 at the center of the mass, and we have the frame E at the tip of the robot. There is only a static transformation between E and 2. And we have these equations of motion that are governing the system. We have two control torques, on tau 1 and tau 2. And we have two interaction torques. Okay, we have two interaction torques, tau 1 and tau 2, that come from the environment. Usually when you're thinking about the environment, we're not thinking in terms of the torques, but we're thinking in terms of what? The wrench, acting on what? At the end effector, exactly. You always think in terms of a wrench. This is a 2D case. So the wrench will become as simple as 3 values. It has a force in the X direction, a force in the Y direction, and what else? There's a rotation, exactly. There's a torque that assume that I have something that's attached here to the end effector, and I'm trying to rotate it, right? So if you imagine that I'm trying to rotate this one, so okay, you can imagine that the rest of the robot arm will start to move. So the wrench here in the 2 dimensions, we're only moving here in 2 dimensions with this planar robot. This is why I have only these 3 values. When I have a 6-dimensional, okay, when I'm moving in 3D, then I have to look at this full 6-dimensional wrench. So recall that the mapping between this interaction wrench applied to the end effector and the torques tau 1 and tau 2, the interaction torques, is given by the geometric Jacobian. So the geometric Jacobian was a map that goes both ways, because it's in one way it's the geometric Jacobian, in the other ways it's dual. And the dual of the geometric Jacobian is nothing else than the transpose of it if we will just work with matrices. So I have here theta 1 and theta 2. When I move theta 1 and theta 2, the end effector will have a velocity. It will have a whole twist. But again, because this is in 2 dimension, it will move in the x direction, and it will move in the y direction. It will also have some sort of angular velocity. I can have these 3 motions of the end effector. So the end effector has a 3-dimensional twist mapped from the 2 angular velocities of the joint. And the inverse, okay, sorry, not the inverse, the dual map will map whatever forces are applied to whatever forces and torques are applied to the end effector through also the geometric Jacobian transpose, and I'm gonna get the interaction torques, okay? So when we're doing interaction, I apply forces to the robot here, and then it interacts with the environment. Okay? So there's some sort, so I apply the torque velocities, sorry. I apply the torque, the joint torques. Then the joints start to move. They start to have an angular velocity. The robot will start to have a velocity. So the end effector will start to have some twist. I'm gonna hit the environment. The environment will gonna be hit back by Newton's 3rd law. I'm gonna have a wrench applied to the end effector and mapped by the Jacobian transpose. I'm gonna have the interaction torques. And again, because of the duality, if I pair these 2, so I take the transpose of this multiplied by that, or the other way around, this transpose multiplied by this will give me mechanical power applied at the joints. And this is the same as the mechanical power applied at the end effector. Okay? So you see, the duality works everywhere. Duality is everywhere. Okay? You want to continue or shall we stop? Stop, okay? Okay, we're gonna continue on Tuesday, okay? So we're gonna be moving on from this, okay? Taking this, okay, but so we're gonna, on Tuesday, inshallah, we're gonna look at the n-dimensional case. If you don't want the 2-dimensional case, which is too easy, we're gonna look at the n-dimensional case, and then inshallah, we're gonna be looking at some extensions of the impedance control. But for now, let's stop and take any questions. And also, I want to ask you for a favor about the feedback, okay? So let me just stop here.